Hello again, everyone. I'm Amanda Wolf, welcoming you back to our series of tutorials for machine learning with AMPL. Today, we're diving into tutorial 6 for comparing models. After experimenting with hyperparameters in the last tutorial, we're taking the next critical step, comparing our various models to identify the best ones. Let's jump in. When optimizing hyperparameters, we generate many models with varying configurations. Each model might perform differently across training, validation, and test datasets. The goal here is to 1. Identify trends in how hyperparameters influence performance. 2. Compare metrics across models to find the optimal configuration. 3. Ensure the chosen model generalizes well to unseen data. We'll now explore AMPL functions to analyze these hyperparameter search results, visualize performance trends, and make informed decisions about the best model configuration. To obtain the variety of models used in this tutorial, all we did was run tutorial 5. But also with some of the bonus parameters outlined at the end of it. Specifically, additional neural network and XGBoost models with fingerprint and scaffold splits were used. While following these tutorials, if you don't want to run that many models yourself, you can use the result_df file saved here. So, AMPL provides powerful visualization tools to help us compare models. The first one, plot train valid test scores, visualizes performance across datasets using line plots of performance scores based on their partitions. Plot hyperperf, plot split perf, plot nnperf, and plot xgperf functions create box plots or scatter plots of performance scores based on their particular hyperparameters. Plot pred versus actual from file plots predicted versus actual values from a trained regression model from each split data subset, that is, your training, validation, and test data. Now, let's get to work. You can see here that we import these functions and necessary libraries. We also suppress warnings. Let's run it. We now need to load in our hyperparameter model results. We can call in all the models with this function here. It scans the specified directory, result_dir, to find the saved models and their performance metrics, returning a data frame, result_df, summarizing the results. Or you can use the example output from tutorial 5 with the prepared functions here. This first function loads a pre-generated example dataset of results. This second one sorts the best performing models. The last one extracts key columns to get an overview of the top models. We'll run these. You see this nice little table pop up. Take note of the different R² values for the different datasets. We'll make a brief table here to count the models for important parameters. In this table, we'll see that ECFP fingerprints and RDKit features, as well as fingerprint and scaffold splitters, were used for each model type. Now, we've got a good number of models here, but not all of them will help us. Certain random hyperparameter combinations result in terribly performing models, which will only mess us up. So let's filter those out, and only keep models with a validation R² score of 0.1 or greater. Here are our results before we filter. You can see the distribution of validation R² scores, including statistics like the minimum, maximum, mean, and quartiles. This is the code that filters. You can see our target R². Let's see our new R² distributions. Here they are. Now, let's reproduce that table from earlier that showed us the number of models per model type to see if anything notable has occurred. Here's the code for the table, like what we saw earlier. We run it. And something has changed. See these NANs? After filtering out the models with very poor metrics, we see that some combinations don't work at all and don't appear in the set anymore. See that decision tree-based models that use RDKit or ECFP features work very poorly to predict on fingerprint split models. In the hyperperf plots module, there are functions that help us visualize the different combinations of features for each type of model. We'll call a function named plot train valid test scores to make a set of broad visualizations to interpret based on R² values, the root mean square error values, and the mean absolute error as well. We fire this function up. And look at all those. We've got some interesting patterns here. Let's look at the R² values first. The R² of the training set metrics are generally higher than the validation and test partitions, which is typical. We can also see that the validation and test scores are similar across many models. This lets us know that they should generalize well to new data. We also see that in general, the model vastly performs the best with the training set every time, whether that means getting the higher R² values or the lower error values. Remember that models can overfit to the training data. But for now, let's focus on these weird peaks here. Now for these fingerprint splits, the model seems to perform better on the test set than the validation set, producing unfortunately high error for validation, whereas we want to minimize MAE or RMS. This tells us that the split is problematic, as the validation set may not accurately reflect the generalization capability of the model. We want validation and test scores to be similar, so if test scores are consistently higher than validation, there may be problems with the data split or sampling. That leads us to want to look at the splits in greater detail. Plot split perf plots the performance of each split type. It's nicely separated by feature type too. So let's run it and take a look. We can see that fingerprint splits have both a lower R-squared and higher error than scaffold splits here, so in general, we can say they perform worse for this dataset. But do notice that RDKit and ECFP features perform differently. ECFP features generally work better for scaffold splits, as we can see by the lower errors and higher R-squared when looking at the ECFP versus RDKit models in the scaffold colors. RDKit features work better for fingerprint splits, which we can see by the same thing. Just a note, as we know from back during the filtering, the RDKit features for fingerprint splits are only represented by neural network models, which might be skewing these results. Let's now visualize how general hyperparameters, like model type and feature type, affect performance. We'll use plot hyperperf, like earlier, but with model type equals general. We run the code. So what we see is that random forests or neural networks perform the best, while ECFP features perform better than RDKit. If we go back to the first, we see that the random forest models perform quite consistently, and there's higher variability with the neural networks in XGBoost. Let's now use plot hyperperf to visualize more model-specific hyperparameters. In this tutorial, we've looked at random forest models in particular, as we have found they generally perform the best for this dataset. Let's run it. Notice the two distinct sets of valid R-squared scores. This is probably caused from the fingerprint versus scaffold split models. Both sets show similar trends, however. With RF estimators, we see that 100 to 150 trees is optimal. RF max depth does okay at the greater end of depth, but worse below about 150. Finally, RF max features doesn't show much of a useful trend, except for these stray dots kind of indicating that below 50 features results in worse models. Say we want to compare a different score type other than R-squared. What are our options? We can use the function to tell. If we run it, we'll see our viable options. For now, let's try mean absolute error. This adjustment is simple. We just use this function, which specifies MAE here. We run it, and we can analyze these graphs just like before. In this next section, we'll look at neural network models and XGBoost models more closely. Neural networks have a large variance in their model performance, which makes it harder to see their important trends as well as the previous methods. So to visualize their hyperparameters, we're going to use plot hyperperf with a subsetted data frame. This will let us look at a single combination of splitter and its features. We'll make those real quick with this code here. You can see that we're only looking at neural networks here for scaffold splits with RDKit. Let's look at what these mean. Average dropout is the average of dropout proportions across all layers of the model. We probabilistically drop out nodes in the network to help regularize and prevent overfitting, helping the model to be more generalizable. Usually, we like a dropout of 0.1 or higher. You can see that we still have a lot of good R2 scores in this desired range. Next, we have learning rate. Recall that the learning rate is simply the hyperparameter that controls how much a model updates its internal parameters, like weights, at each step during training. Generally, learning rates that are about 0.01 do best, and you can see that our distribution here has a few points at this desired rate. Next is num weights. This is the product of layer sizes, plus the number of nodes in the first layer, which gives a rough estimate of total model size, or complexity. We want this parameter minimized by selecting the smallest layer sizes possible that still maximize the preferred metric. You can see quite a few points on this low end. Num layers is simply the number of layers in the neural network, which also tells us about complexity. We also want this one minimized. Then we have best epoch. Best epoch visualizes which epoch resulted in the highest performance. Recall that an epoch is one complete pass of the training dataset through the algorithm. If the best epochs are very small, it hints at problematic, non-thorough training. Then we have max epochs. This is the max number of epochs that the model was allowed to train on. Now, something called early stopping may have occurred. This is when overfitting is prevented by stopping a model's training process when its performance on the validation set begins to decline. But if the max epochs is too small, you may have underfitted your model. We can tell if it is too small if all of our best epochs are at max epoch. As promised, we're also talking about XGBoost models. There are two main parameters that we want to visualize for XGBoost models, which are learning rate and gamma. With plot XGPerf, we can simultaneously visualize them. We see a trend right away, at least for the learning rate. If we look further, we see that XGB learning rate should be between 0 and 0.45, because after this range, the performance deteriorates. Now, there's no clear trend for XGB gamma, but if you'd like, you can use the plot Hyperperf function to visualize even more parameters for XGBoost. Remember back in tutorial 5 when we called in compare_models from the library? Now, once we use compare_models.get filesystem_perf results, which is visible here, we can sort the data frame to the score we actually care about. Here we establish that we want it based off of the validation R² scores, and that we read the CSV file, sort out by our winning score type, and then make a neat table with this line to display the results of our top models. Like so. Remember that if testing other score types, you want mean absolute error and root mean squared error to be minimums, not maximum. Now, if you don't want a table and just want to get the top model and its information, try this code here. We can do similar functions here to find other model information, such as dropouts, learning rates, and model paths. And there we go. Now down here, we use plot, pred versus actual from file. This will let us visualize prediction accuracies. So our best model right now is a neural network model. We get these three graphs about it for the training, validation, and test data sets. But we have to be careful about selecting models only based on their performance metrics. As we are about to see, this best model has problems, even with the R² score being fairly high. Firstly, we see that the model does not perform well at PKI values below 4.5 for any of the data sets. Also, we can see the odd bits of data at PKI equals 5. This data is censored, meaning in this case, all we know about the compounds is that they have a PKI less than 5. Higher concentrations of drug were not tested, and this data is rather poorly predicted by the neural network model. So let's call upon our best random forest model instead, and see if it works better than the neural network model. We use this code here, and call upon plot, pred versus actual from file again. We run it, and here we are. Note that though the performance at R² value is lower for this model, the graph visually shows better prediction, especially in the crucial lower range where the neural network models failed. The random forest model also does better at the part where the data was censored. This model seems pretty good then, but let's check our top XGBoost model, just to be sure. Once again, we call upon similar code, tailored for the XGBoost model. We can see pretty immediately that this model, while it predicts the low-end PKI values better than the neural network model, still has trouble with the censored data. So, after all that, it looks like we should go with the random forest model. That wraps up our deep dive into comparing models. We've learned how to filter results, visualize trends, and evaluate individual models to make informed decisions. In tutorial 7, we'll use the best performing parameters to train a full production model with the entire dataset. Thank you for watching, and see you there.